Hi Year 12. Let's have a look at your lesson 5. So this was all about looking at how we combine uncertainties when we complete calculations with data that have different uncertainties. So task number 1. The answers were on the slides, but I just want to show the working for you in case you weren't sure. So question 1 was very straightforward. You just had to find the uncertainty as a percentage of the value. So you find the ratio and then you multiply by 100. And so those were your percentage uncertainties. So you can pause if you need to, but that was just to get us started. And then it asked you to calculate the value of A plus D. So obviously we're given the values at the top. A was 2.55, D was 5.35. When we add those together we get 7.9, so that's the value. And then when we are adding data, we add the absolute uncertainties. So we add the uncertainty of A to the uncertainty of D, and we get plus or minus 0.06. And it's a similar process for question 3, just with C and E instead. Now, one thing to notice is that I don't need to write the unit twice. Because both of these values are in millimetres, I can just write it at the end. What you'll notice is when we have to write percentage uncertainties later, the unit has to go next to the value because we don't have a unit after the percentage. So again, just add the two values, C plus E in question 3, and then the absolute uncertainties are 0.1 plus 0.2 to get your final answer. So those were quite straightforward. It was only later on that got a little bit trickier. So percentage uncertainty of A multiplied by D. Well, firstly, let's find the value. It's 13.6, just multiply numbers together. And when we are multiplying data, we add their overall percentage uncertainties. So we'd worked out in question 1 the individual, and then we just add the percentage of A to the percentage of D to get our total value. In question 5, it steps up a little bit again in difficulty because we've got B divided by A squared, which means because we're raising A to the power of 2, we get 2 lots of the percentage uncertainty in A factoring in. Plus, because we're dividing these two things together, we have to add the combined percentages. So we've got the percentage of B plus the percentage of A squared, and A squared was 2 lots of the percentage of A. And again, it's just plugging numbers in at that point. Pause if you need to look at my working. And then it's back to basics, A multiplied by B value. We add the percentage uncertainties that we calculated in question 1, and we quote it as you can see here. A over E squared, again, it's A plus 2 lots of E percentage uncertainty, and that gets us our overall value. Lastly, in question 8, firstly find the value of A plus D over C squared here. Now in question 2 we worked out the absolute uncertainty of A plus D, so we worked that out, if I go back up, to be 0.06. 0.06 out of the 7.9 that is A plus D works out to be 0.76%. So I firstly converted my answer in question 2 to be a percentage value, because I have to add the percentage of A plus D to 2 lots of C, because I've got C squared. So I needed to do multiple steps there. But remember, you cannot combine absolute and percentage uncertainties. So take a pause if you need to before we have a look at the next task. So task 2 was just more practice really. For each of the questions, show your working, write your answers in the box provided. Now I actually had done these separately, so rather than me write them out again, I'm just going to refer to them to save myself a little bit of time. So we've got the absolute uncertainty here. This is just a case of finding the absolute uncertainty as a fraction of the value, and then to convert it from a fractional uncertainty to a percentage we multiply by 100. please could you self-assess as you watch this video, and if you get them wrong, just pause, make corrections. It'll be much quicker than uploading for me to have to see and mark and get back to you. So seeing as you can see the work solutions, could you please self-assess as we go through? B is a similar situation. You've got the absolute uncertainty in the value, find it as a ratio. Don't forget to multiply by 100% into percentage. You should have got plus or minus 0.8% there. In question 2, I'll fold this over actually, might be a good idea. So in question 2, you're given the percentages and then you just need to find the absolute uncertainties. So you're literally finding 10% of this number. Now it's just a tenth, isn't it? So it's just a tenth of this is going to be 0.35. So that one was pretty straightforward. There's your absolute uncertainty for 2A. In 2B, obviously it's not quite as simple as just tens. So we find 1% of the value by dividing by 100. And then we multiply by the percentage that we have. So 16 over 100 is going to be 1% of this value. We multiply it by 8, and that gets us our plus or minus 1.3 seconds. Okay. In question 3, it's not just as simple as one value, we've got some combinations. So in A, you can see, sorry, let it just sort itself out. We add the two values firstly. 2.7 plus 12.02 gets me 14.72. And when I'm adding data, I just add their absolute uncertainties. So 0.05 plus 0.08 gives me 0.13 as my absolute uncertainty. Okay, in B, 2.7 minus 12.02 is minus 9.32. Now don't forget that errors always accumulate even if you're subtracting. Okay, this is our level of uncertainty. We can't get more certain, so we still have to add our 0.05 and our 0.08. So we've got the same uncertainty in B. In C, you've been given a mixture of absolute uncertainty and percentage uncertainty. So we're just adding the numbers together firstly. 3.5 and 2.7 gives me my 6.2. I know that 10% of 3.5 was 0.35. We worked that out in part 2A. And then I just take my absolute uncertainty conversion and I add the two together, giving me my 0.4. In question 4, let's see if I can fit this all in. We're multiplying data. Okay, so if we're multiplying two values, we have to add their percentage uncertainty. So the first thing we have to do is find the absolute as a percentage of this, and again for this one as well. So 0.05 over 2.7 multiplied by 100 gives me a 1.85% uncertainty in 2.7, and similarly 0.08 over 12.02, multiply that by 100, gets me a 0.8% uncertainty in my value there. I then multiply these two numbers together, because that's what I'm actually looking for, gets me 32.45, and because I've multiplied, I add the percentage uncertainties together, so this one plus this one makes my plus or minus 2.65%. Okay, in B we are dividing, but again, just as with subtraction, even though our value was obviously via dividing, we still have to add our percentage uncertainties. Okay, we are accumulating errors. We have to account for both errors. So again, we need to convert our absolute uncertainty into a percentage. We'd actually already worked this out in the previous question. So we've actually got 0.8%. Plus the 8% from the 16, therefore my value of 0.75 coming from 12.02 divided by 16 is going to be plus or minus 8.8% there. Okay, in C we've got a value multiplied by another value divided by another value. We are literally going to do 3.5 times 2.7 divided by 16. That's our value. We're going to firstly convert this absolute uncertainty into a percentage. I think we've already done that previously, but we can do it again, no problem. Errors are still going to accumulate. Okay, so we've got A times B divided by C. We are going to add the percentage uncertainties of all three bits. So we've got 10% for the first bit, 1.85% for my percentage of the 2.7. Go back if you need to 1A to check that one, and then plus my 8%. So I've got my value of 0.59, and then I add the three percentage uncertainties together. So you can see that as we manipulate more and more data, and more data is contributing to our final answer, our uncertainty in our final answer is going to go up significantly. Now this is quite a large uncertainty. Then let me see if I can just move this down. Ooh, a bit wobbly. So question 5, we've got two lots of 2.7 plus or minus 0.05. Now think about it, we could actually express this multiplication as an addition. If we've got two lots of this, that's the same as writing 2.7 plus or minus 0.05 plus 2.7 plus or minus 0.05. So we find our value of 5.4, and because we have two lots and we're adding two lots of these, we add these absolute uncertainties. Okay, so here when we just scale by a factor, we're actually just going to gain two lots of my absolute uncertainty as well. Okay, so hopefully you can see how I've got 5.4 plus or minus 0.1. Okay, in B we've got two lots of 16 plus or minus 8%. So I found 8% as an absolute uncertainty. That's important. Okay, so I've got two lots of 16 plus or minus 1.3. That is 8% of 16. And again, I've then got my uncertainties in a way that I can accumulate them. I've got 1.3 plus 1.3 gives me plus or minus 2.6. Okay, now interestingly, and hopefully this will make sense to you, if I find 2.6 as a percentage of 32, I get 8%. Now you should notice that that is the same percentage, because actually all we're doing is we're scaling our value. Okay, if we've got two lots of something with a particular absolute uncertainty, the percentage error is not going to change. Okay, so that's worth making a note of. Okay. In part C, we are squaring our value. Okay, so instead of this being like the previous one where we multiplied by a value and said that that's the same as adding that many of them, if we're squaring our 12.02, that's the same as writing out in full 12.02 multiplied by 12.02, and each of those has its own absolute uncertainty. Okay, but because we're multiplying data, to find the accumulated percentage uncertainty, we have to first have the percentage uncertainty of both of them. Okay, so we do 0.08 over the 12.02, multiply that by 100. I now know that this as a percentage is 0.8%. And then, because I'm multiplying these two together, I add their percentage uncertainties, and 0.8 plus 0.8 is my 1.6%. Okay, just move a few things around here. Alright, density is the ratio of mass to volume. So we can write that as density is mass over volume. And it asks, what is the density of a material if m is 12.4 kilograms and v is 6.68 meters cubed? Determine the least uncertainty in the mass and the volume and calculate the uncertainty in the density value. And then make sure you've got the right number of significant figures. Okay, so firstly, let's find our value. So we've got the mass of 12.4, we've got the volume of 6.68. You should have been able to get that the density is 1.86 kilograms per meter cubed. Okay, both values are 3 significant figures, so I can quote this to 3 significant figures. Now, the uncertainty, if not stated as being measured, is going to be the precision of the value. Okay, the fact that I could only record this to the nearest 0.1 kilograms says that I'm not sure by that much. Okay, I can't be more certain than the nearest 0.1 kilograms. And then again, for volume, my number of significant figures tells me the precision of the instrument. Okay, so I know my absolute uncertainties in my mass and my volume purely by looking at how many decimal places I've got, basically. Now, obviously, this is when we don't have repeat readings, and this is the instance where we take the precision. So what I did is I found this as a percentage of this, and got 0.8%. This value as a percentage of this value is plus or minus 0.15%. Now, density comes from dividing mass by volume. When we divide data, we add their percentage uncertainties. So all I've done is I've added these two together to get my total uncertainty and my density. Okay. So question 2, what is the uncertainty in the calculated area of a circle whose radius is to be determined? Quote the area and its uncertainty as well. So let's have a look at number 2. You should know from maths that the area of a circle is pi r squared. We are given the radius of the circle and its absolute uncertainty, 0.5 out of 14.6. Multiply that by 100 gets me the percentage uncertainty of 3.4%. If I find r squared, so 14.6 squared is 213.16, I'm going to have 2 lots of the percentage uncertainty. So 2 lots of 3.4 is 6.8. Okay, so I now have my percentage uncertainty in r squared. I'm going to need that because the area that I calculate comes from pi and r squared. Now, pi is just a scale factor, just like we had in the previous question. So this doesn't influence how uncertain I am at all. Only the r squared value contributes an error. So the percentage uncertainty in r squared is also the percentage uncertainty in the area. So that's how we calculate number 2. Okay, question 3. We've got a resistor with a 2% tolerance. That's just a fancy way of saying plus or minus 2%. We can find that as an absolute value. 2% of 1800 is 36 ohms. We're told that the resistor has a label on it that says it's 1800 ohms. What is the range of acceptable values that the resistor might have? So what this means is when we buy resistors from factories and companies that make them, they can state to us that this is the resistor that we're buying, but that it could be plus 2% or it could be minus 2%. So therefore, it may actually be as low as 1764, or it could be as high as 1836. Okay. So that's what we mean by the tolerance. So then it gives you a value of the current. It says 2.1 plus or minus 0.1 milliamps. Don't forget your milli there, means times 10 to the minus 3. We can find 0.1 as a percentage of 2.1. It's 4.76%. And that is therefore going to help us with our voltage. So we should know from GCSE that V equals IR, voltage is current multiplied by resistance. We're literally going to take our values and multiply them together to get 3.78 volts, but to 2 significant figures because of our limit from our current. And then what we're going to do is we're going to add the percentage uncertainty in each value, because we're multiplying the data, we have to add their percentages. So the 4.76% plus the 2% gives us our overall uncertainty in V. Okay. Next up is number 4. So we've got an accelerating object has an initial speed of 12.4 plus or minus 0.1 milliseconds. I've converted that immediately to a percentage. I know it's going to be helpful. I've got a final speed V of 28.8 plus minus the absolute uncertainty. I've converted that to a percentage. By now you should be familiar with this. And again, I've done the same for the time. Okay, I'm then asked to find the acceleration. So again, we should remember from GCSE that acceleration is change in velocity over time taken. So I can express that as V take U divided by T. Okay, so we need to take this in 2 steps. Because we're subtracting data in the brackets, we need to combine their absolute uncertainties. So I've done V take U gives me 16.4 as a value, but the absolute uncertainty is the sum of the 2, plus or minus 0.3. But I then am going to need to convert that to a percentage because I'm dividing that by T, and to divide data we have to add their percentage uncertainties. So I find 0.3 is a percentage of 16.4. Then I find my acceleration value by plugging in the values that I have. Hopefully that's pretty obvious what I've done there. 3.9 meters per second plus or minus now the percentage uncertainty in T that I found here, and the percentage uncertainty in V take U, which came from my absolutes. So hopefully this is starting to make sense, how to combine all of these different examples. I think this is the last one, fingers crossed. The volume and its uncertainty for a sphere. Again, this is an equation not in your data booklet. It is expected that you know the volume of a sphere. V is 4 over 3 pi r cubed. You're given the radius. So initially I found the percentage uncertainty from the absolute, so 1 over 21 multiplied by 100. I know that in my volume I have r cubed, so what I want to do is find the percentage uncertainty in r cubed. So I've got 3 lots of the percentage uncertainty in r, giving me my 14.3%. Okay, I'm then going to plug my values in to get the volume, 4 over 3 pi r cubed. It gives me my value in millimeters cubed. I then quote that to 2 significant figures because I've only got 2 in the question, and I can then quote with my overall percentage uncertainty. So remember that 4 over 3 has no uncertainty associated with it, it's just a scale factor, and the same for pi, so there's no uncertainties to accumulate. The only uncertainty in the volume comes from the fact that we have some uncertainty in r cubed. There we go.